Welcome to Chapter 28, Part 2.
Einstein had some ideas about this. It's called the photoelectric effect. And it's written out like this. K max equals E minus E0. K max is the electron's kinetic energy. K max is the electron's kinetic energy. E is the electron's energy from the photon. So this is the energy that the photon gave to the electron in the metal. EO, or E0, this is called the work function. This is the work function of the metal. The work function is the energy needed to free an electron from a metal. The energy needed to free an electron from a metal. We're going to start with the energy that the light gives to the electron, EE. This energy is equal to Planck's constant times the frequency. So we say that EE is equal to HF. There are two ways that we can represent Planck's constant. The first one is H is equal to 6.63 times 10 to the minus 34 joule seconds. The other way that we have is we say that H equals 4.14 times 10 to the minus 15 electron volt seconds. Remember that an electron volt is another way to measure energy. We touched on that in chapter 21 or 22. Which value you use is going to depend on context. We also treat light as a particle here, mostly because it's easier and it seems like we're making this up as we go anyway, so why not? Now that we have EE, we can work on finding E0, the work function. We established previously that electrons are ejected starting at a threshold frequency FO, or F0. So we say that F0 is equal to H times the threshold frequency. We now have EE and we have EO. Now, let's get this into a form that involves the stopping potential. We started out with K max is equal to EE minus E0. Again, so this is the ultimate energy of the electron is equal to the energy given to the electron by the photon minus the work function, where the work function is the amount of the energy that's required to take the electron off of the metal at all. Rewrite that as K max is equal to HF minus HF0. And now we're going to go back to an equation that we got on the last page. We're now going to represent K max as E V stop. That is going to equal HF minus HF0. Do some algebra. We get that V stop is equal to H over E times F minus F0. And we are able to get a value for the stopping potential. Our stopping potential is going to be equal to H over E times delta F. Einstein actually won the Nobel Prize in physics for seeing that. Not for general or special relativity as most people think. On a somewhat related topic, we now move to matter waves. We know that light behaves like a wave and a particle. So I can only imagine that this de Broglie guy got turned one night and thought that matter might behave like a wave too. He was actually onto something. The wavelength of any massive particle can be described based on its momentum. We say that lambda is equal to h over p, where p is momentum. This is the same momentum as we were dealing with before. So we say that h, that's equal to h over mv. That is how you find the wavelength of something. We can find the wavelength for anything with mass and momentum. We're going to do that for an electron, a proton, and a baseball, all with a kinetic energy of 1 electron volt. Let's take a minute to think about which values we know and how we can find the others. So when we think about what values we know and what values we can find, let's start with mass. I gave you the mass of a baseball because I guess that's not something that most people have in their minds already. Which makes me wonder, what do people think about? Anyway, the mass of an electron is 9.11 times 10 to the minus 31 kilograms. That one you should know. The mass of a proton, which you might not know, but you should probably have on your formula sheet or look up, is 1.67 times 10 to the minus 27 kilograms. That should be on your formula sheet. So we have those masses. We also were told that each of these has a mass of, each of these has an energy of 1 electron volt. The equations that we're going to be operating, so we want to find velocity and wavelength. When we are finding to find velocity, we're going to want to use the energy value. For velocity, we're going to be using K equals 1/2 mv squared. There's one thing to keep in mind though while we're doing this. The energy values that we were given are in electron volts. this equation is designed to work with joules. To go between electron volts and joules, again, we did this in chapter 21 or 22, but as a recap, 1 electron volt is equal to, written down, 1.6 times 10 to the minus 19 joules. 1.6 times 10 to the minus 19 joules. Now we have that. And we had to convert that because this equation is designed to work. This equation gives you an energy that's in joules. So if you're using this, you've got to be using joules. So let's find these velocities. We're going to start with, for the electron, we have 1.6 times 10 to the minus 19 joules equals 1/2, 9.11, 10 to the minus 31 kilograms times velocity of the electron squared. We get velocity of the electron to be 5.9 times 10 to the 5 meters per second. Now we can do the rest. Try the other velocities on your own.
And we will look at the wavelengths in part 3. See you then.